Pluto is a distant and mysterious dwarf planet, once a member of our solar system's planetary family. However, current startling announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning revelation. They suggest that this icy world is on a collision course with Neptune. But how could this happen, and what might be the consequences of such a big event? Are we witnessing a rare astronomical phenomenon? Or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune effect. Pluto, a former planet demoted to a dwarf planet partially due to its odd orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the red flag of a possible dangerous collision between these two planets, which poses a significant risk to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a whopping 248 years to complete a single orbit, which means that since its discovery in 1930, it hasn't even completed one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, angled 17 degrees to the ecliptic plane. The course Pluto traces is much steeper compared to the other planets. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 2 decades in every orbit, Pluto actually comes closer to the Sun than Neptune, defying what we'd expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacy of space mechanics. The three-body problem in space is about figuring out how 3 things in space like Pluto, Neptune, and the Sun move and influence each other with their gravity. Pluto's orbit is technically chaotic. Minor deviations in initial conditions lead to large differences over millions of years. But these unique properties of Pluto's orbit have been found to maintain stability over exceptionally long timescales, effectively keeping chaos at bay. Recent computer simulations have helped us understand how the giant planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Jupiter's gravity alone is strong enough to keep Pluto on a stable path for a very long time, possibly even billions of years. These phenomena are crucial in maintaining the order and predictability of space's movement. Without these mechanisms, the solar system as we know it would be a place of much more chaos and unpredictability. Pluto's orbit is a prime example of celestial mechanics at play, demonstrating both stability and chaos within our solar system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, especially Neptune, showcase the complex and dynamic nature of space. Predicting cosmic events, especially when it involves chaotic orbits like Pluto's, poses significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainty. While numerical simulations offer a powerful way to understand and predict the future paths of celestial bodies, they also highlight the limitations in our predictive abilities. So why are major astrophysicists only now raising concerns about a possible collision between Pluto and Neptune? Despite all these complex forces trying to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both prominent figures in astrophysics, have expressed concerns about a potential collision between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a rare and catastrophic event in our solar system. The collision would release an enormous amount of energy, likely shattering Pluto given its smaller size and icy composition. Debris from the collision could scatter across the solar system, potentially creating hazards for other planets and their moons. For Neptune, such an impact could alter its environment and possibly its orbit, depending on the specifics of the collision. Michio Kaku, a renowned theoretical physicist known for his work in string theory, brings a unique perspective to the debate as well. His views on the future of space exploration and the interaction between celestial mechanics and theoretical physics provide deep insights into the mysteries of space phenomena like Pluto's orbit. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto can provide valuable insights for future space missions. This knowledge can help in navigating the solar system more efficiently, predicting potential hazards, and even in the planning of missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to explore other celestial bodies, providing a blueprint for how we might approach and understand distant worlds. When it comes to the physics of planets, celestial mechanics, and theoretical physics are deeply interconnected. The actions and interactions of planets, including the gravitational dance between Pluto and Neptune, are linked to the fundamental principles of physics. If Pluto and Neptune were to collide, it would be a monumental event in astrophysics, providing a unique observational opportunity that could potentially relate to string theory. String theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional strings, seeks to explain the fundamental forces and matter in the universe. The collision could produce extreme conditions of energy and gravity, potentially creating scenarios where predictions made by string theory could become observable. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be profound. It could potentially contribute to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's enigmatic dance around the Sun continues to captivate scientists and enthusiasts alike, providing a window into the complexities of planetary systems. While its reclassification as a dwarf planet sparked debate and redefined our understanding of planetary bodies, recent revelations about its orbit have reignited interest in its role within the solar system. Neil deGrasse Tyson and Michio Kaku, two distinguished voices in astrophysics, have raised concerns about a potential collision between Pluto and Neptune, shedding light on the intricate dynamics at play in our cosmic neighborhood. Their warnings underscore the importance of understanding the gravitational interactions and orbital mechanics that govern celestial bodies' movements. Pluto's orbit, characterized by its eccentricity and steep inclination, defies conventional expectations and challenges our comprehension of planetary motion. Unlike the highly circular orbits of its neighboring planets, Pluto's path traces a unique trajectory intersecting with Neptune's orbit at points during its long journey around the Sun. The gravitational influence of other planets, especially Neptune, plays a crucial role in shaping Pluto's orbit and maintaining its stability over millennia. Despite the chaotic nature of its trajectory, numerical simulations and theoretical models play a vital role in predicting the future paths of celestial bodies and understanding the complex interactions between planets. These simulations indicate that while Pluto's orbit is chaotic over millions of years, it remains dynamically stable within the broader framework of the solar system's gravitational field. The potential for a collision between Pluto and Neptune, as suggested by astrophysicists Neil deGrasse Tyson and Michio Kaku, highlights the ongoing uncertainties and complexities in planetary dynamics. While such an event remains hypothetical and highly unlikely in the near term, the gravitational dance between Pluto and Neptune underscores the delicate balance of forces that govern the celestial bodies within our solar neighborhood. Beyond its scientific significance, Pluto's exploration offers practical insights for future space exploration missions. The New Horizons spacecraft, launched by NASA in 2006, provided unprecedented images and data of Pluto and its moons during its historic flyby in 2015. The mission revealed surprising details of Pluto's surface features, including mountains of water ice and vast plains of frozen nitrogen, enhancing our understanding of the geological processes shaping the remote dwarf planet. The success of the New Horizons mission underscored the technological advancements and collaborative efforts required for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the diversity of planetary bodies and the environmental conditions present in the outer regions of the solar system. These discoveries have implications for future missions to explore other dwarf planets and trans-Neptunian objects, advancing our understanding of planetary formation and evolution. Pluto's classification as a dwarf planet has also sparked discussions about the criteria used to classify celestial bodies in the solar system. The debate over planetary definitions reflects broader questions about scientific classification systems and the evolving nature of astronomical knowledge. While Pluto meets some criteria for planetary status, such as orbiting the Sun and having enough mass for self-gravity, its classification as a dwarf planet highlights the diversity of planetary bodies beyond the traditional 8 planets. The exploration of Pluto's orbit extends our knowledge of celestial mechanics and planetary dynamics to the outer reaches of the solar system. By analyzing the interactions between Pluto, Neptune, and other celestial bodies, scientists can gain deeper insights into the formation and evolution of planetary systems. These insights are critical for developing theories about the origins of our solar system and understanding the processes that shape planetary bodies over billions of years. Pluto's discovery and subsequent exploration have contributed to our understanding of planetary migration and the formation of the Kuiper Belt, a region beyond Neptune populated by small icy bodies. Studying Pluto's orbit provides clues about the gravitational interactions that may have influenced the migration of planets during the early stages of solar system formation. These studies provide valuable insights into the dynamics of planetary systems and their evolution over cosmic timescales. In conclusion, the study of Pluto's orbit represents a milestone in our exploration of the outer solar system and beyond. By unraveling the mysteries of Pluto's composition, orbital dynamics, and geological history, scientists can gain valuable insights into the formation and evolution of planetary systems. These insights are essential for advancing our understanding of celestial mechanics, planetary dynamics, and the broader context of planetary science. Pluto continues to inspire scientific inquiry and exploration, offering a window into the complexities of planetary systems and the diverse range of celestial bodies that populate our solar system.